When the James Webb Space Telescope finally turned its mirrors toward Andromeda's heart, it wasn't looking for drama. It was looking for confirmation. Instead, it found contradictions. Today, we explore what Webb actually saw inside our nearest galactic neighbour, how generations of scientists slowly uncovered the clues that led here, and why the data now suggests Andromeda is not what we thought it was. This isn't speculation. This is measured, verified, hard-earned science, and it took humanity more than a century to reach this moment. So sit back, relax, and let me show you what Webb has just uncovered. In astronomy, expectations are not guesses. They are slow agreements, built year by year, image by image, across generations. And for more than a century, optical telescopes kept telling a steady story about the core of the Andromeda galaxy. It looked settled. It looked old. A crowded bulge of stars. Yes, but not a place that seemed to be doing anything dramatic. No obvious fireworks. No loud signatures of violent change. So when astronomers turned the James Webb Space Telescope toward Andromeda, the goal sounded almost modest. Map the dust, count the stars, trace the structure that visible light had already outlined, only with sharper detail and deeper reach. That effort carried a quiet confidence. If the core was truly calm, Webb would simply confirm it, only more beautifully. The near-infrared camera would separate starlight from the haze, measuring which stellar populations lived where and how that population changed with distance from the centre. The mid-infrared instrument would do something optical telescopes could not do cleanly. It would measure dust by its own heat, by thermal emission, reading temperature like a fingerprint. Together, the plan was straightforward, a careful inventory, a better map, a deeper look at something already understood. Then Webb delivered the first payoff, and it did not feel like an improvement. It felt like a contradiction. Near the core, Webb detected dust that was not merely present, it was glowing. In infrared, glow is not decoration. Glow is physics. It is matter radiating energy because it is warm. And warmth in a galactic core is not supposed to appear by accident. If there is heat, something is feeding it. Something is stirring it. Something is happening, whether the eye in visible light admits it or not. The infrared view showed heat where none was expected, and suddenly the century of calm looked less like truth and more like a limitation of the way the story had been told. Even the dust itself seemed to change personality. In optical images, dust often appears as darkness because it blocks and scatters visible starlight. But Webb revealed dust rings that appeared bright instead of dark. That is the unsettling detail. A ring that looks dark is a curtain. A ring that looks bright is a source, or at least a surface warmed enough to announce itself. The moment those bright rings emerged, the core stopped being a quiet backdrop and started behaving like a system with structure, with layers, with an internal logic that had been hidden. The deeper facts followed quickly, because Webb is not just a telescope. It is a set of instruments designed to cross-examine a scene from different angles. The near-infrared camera measured the stellar populations, separating older stars from regions where different kinds of stars dominate, letting astronomers ask whether the centre is as uniformly ancient as it once seemed. The mid-infrared instrument measured the dust temperature through thermal emission, turning the glow into a diagnostic. And the most telling clue was not a single warm spot, it was a pattern, temperature gradients, subtle shifts from hotter to cooler across the rings and inner regions, like a topographic map of energy. Gradients imply flow, they imply sources and sinks. They imply that the centre is not merely sitting there, collecting starlight like a museum. Something inside is injecting energy, or reshaping the environment in a way that creates pockets of warmth and organised rings. That is the first sign that the core is dynamically active. Not necessarily violent, not necessarily bright in the way optical telescopes trained us to expect, but active in the way that matters most for understanding a galaxy, active enough to leave heat behind. So the question changes. If Andromeda looked quiet for 100 years, what else has been quietly active, only speaking in wavelengths we were not listening to? And if Webb can expose heat where none was expected, What will happen when we follow that heat to its source? We ended with a quiet discomfort. Heat where none was expected. Dust rings shining when they should have been shadows. And the question that hangs in the air is almost unfair. If this activity was real, how did astronomy miss it for so long? For most of modern history, astronomers built their understanding of galaxies with visible light. It made sense. Visible light is where stars shine brightly, where photographs look intuitive, where the night sky feels familiar. So the core of the Andromeda galaxy was studied again and again with optical telescopes, and the results seemed consistent. Crowded starlight, smooth structure, nothing that looked like a system being fed with fresh energy. But the core sits behind dust. Not a dramatic wall, not a single cloud, but a complex veil that scatters and absorbs visible wavelengths. Dust does not have to be thick to distort a story. It only has to sit in the right place. And when visible light tries to cross that region, some of it never arrives. Some of it arrives altered. That means the darkest parts of the core can look empty even when they are full, and the quiet parts can look quiet simply because their signal has been filtered out. Scientists still did careful work. They used photometry to count stars and measure brightness patterns, building statistical portraits of the stellar populations. They used spectroscopy to measure motion, reading small shifts in starlight to map rotation and velocity. But spectroscopy in visible light can tell you how stars move while staying blind to something else entirely. It cannot easily reveal hidden heat if the heat is trapped in dust and cold gas that barely speaks in optical wavelengths. Then came the shift Webb made possible. Infrared wavelengths do not play by the same rules. Infrared can pass through dust far better than visible light, not because dust disappears, but because the interaction changes with wavelength. Suddenly, the core is not a scene viewed through smoke. It is a scene viewed with a different sense entirely. Infrared also detects what visible light barely notices. Molecular vibration. Warm dust emitting its own radiation. Chemistry leaving signatures in absorption and emission. And Webb stretches far into that range, observing out to about 28 microns, reaching wavelengths where cold gas and dust finally become visible rather than merely obstructive. That is why the hidden structures emerged so fast. They were not newly created. They were newly revealed. Rings that looked like absence became bright features. Temperature variations became readable. And infrared spectroscopy started to expose chemical signatures that were effectively missing from the old record, as if decades of observation had been looking at the same book but skipping every page written in a different ink. So the mystery is no longer why Webb found something new. The deeper mystery is why we trusted a century of sight without asking what the dust was hiding. And once the veil lifts in Andromeda, the mind cannot avoid the next question. How many other galactic cores have been called quiet, only because we listened in the wrong language? After Webb showed us that Andromeda's core is not as quiet as it looked, a second thought arrives almost automatically. Even if the core were perfectly calm, would that really make Andromeda harmless? A galaxy can be silent and still be moving. For a long time, Andromeda was treated like a distant landmark, something to measure and admire. Early work focused on what the eye could compare, its size on the sky, its brightness, its pale shape stretching across the darkness. Distant, yes, but in the mind, also static, as if distance itself meant separation. Then astronomers did something more demanding than describing. They measured. Edwin Hubble used Cepheid variable stars as distance markers, the kind of stars whose regular brightening and dimming can be turned into a cosmic ruler. That effort changed Andromeda from a smudge into a location, roughly 2.5 million light-years away, not inside the Milky Way, but far beyond it. And once a galaxy becomes a real place, the next question becomes unavoidable. What is it doing? Spectroscopy gave the answer, not by taking a photograph, but by reading light like evidence. The lines in Andromeda's spectrum were shifted towards shorter wavelengths. A blue shift. The kind of shift that means approach, not retreat. And the approach is not poetic, it is measurable. About 110 kilometers per second toward the Milky Way. Now consider what is moving. Not a ship, not a star. A galaxy with about 1 trillion stars. spread across a diameter near 220,000 light-years, a structure so large that even its emptiest regions contain suns, and gravity binds it to us, tying two massive systems into the same long conversation. So the payoff is unsettling in its calmness. Andromeda is not simply out there, it is on a path. The deeper fact is even stranger. When Webb finds activity in the core, it is not happening in a distant museum. It is happening in an approaching neighbour, and the word inevitable starts to feel less like drama and more like physics. Does this motion mean collision? Or does it mean something slower, more complex, more beautiful? A long-term interaction written by gravity, already underway. The approach of Andromeda stops feeling abstract. A whole galaxy is moving toward us, bound by gravity, already committed to a shared future. But motion raises a sharper question. What sits at the centre of that moving system? What kind of engine is Andromeda carrying? For decades, astronomers treated the black hole in Andromeda as dormant. The core did not blaze with obvious activity. There were no dramatic outbursts that demanded attention, so the simplest label stayed in place. Quiet, minimal, sleeping. Yet the effort to test that assumption did not begin with looking for light. It began with watching stars. Track them long enough, and their paths become a kind of confession. The Hubble Space Telescope resolved the nuclear region and followed the stars near the centre over time, not as a blur, but as individual points with measurable motion. And in that motion, a pattern emerged. Orbits that curve too tightly, too quickly, around something you cannot see. This is where the payoff arrives, almost coldly. When stellar orbits are mapped, the hidden mass can be calculated using Keplerian dynamics. If a star swings around an unseen centre at a certain speed and distance, the mathematics tells you how much mass must be enclosed, and for Andromeda, that mass is extreme, about 140 million times the mass of the Sun. Now, the deeper facts turn the mind uneasy. An event horizon larger than the orbit of Mars is not a metaphor, it is a scale, a region so large that a planet's path would fit inside the boundary, where light cannot escape, and this black hole is about 35 times more massive than the one in the Milky Way. It is not merely a central object, it is a dominant feature in the inner gravitational architecture. For a time, there were questions about whether the centre might contain two black holes, a binary system left behind by an ancient merger, but the evidence pointed to a single black hole, not a pair. One central mass, one deep well. And now, after Webb shows warmth and structure where the core was expected to be still, the old word dormant begins to wobble. If the black hole is truly quiet, why does the dust look energized? If the dust is energized, what is feeding it? And if something is feeding it, how long has the centre been active without announcing itself in the ways we trained ourselves to notice? We have been circling the same suspicion since Webb saw warmth in dust that should have been cold, and since the central black hole stopped sounding truly asleep. But suspicion is not evidence. For that, astronomers needed a different kind of light, the kind that appears only when matter is heated to extremes. For years, the expectation was simple. If the black hole in Andromeda was dormant, its core should show steady, weak X-ray emission, a low background level from hot gas and scattered high-energy processes, so the core was monitored, patiently, across decades. The Chandra X-ray Observatory became a watchtower for that invisible sky, sensitive to high-energy photons that optical telescopes cannot register. A baseline was recorded from around the year 2000 onward, not dramatic, just consistent enough to be comforting. Then the payoff arrived in the most unsettling form, a sudden flare detected in the year 2006. The X-ray brightness jumped by roughly a factor of 100, not a gentle drift, a leap, the kind of leap that forces a reconsideration of every calm label placed on the system. If it had ended there, it might have been dismissed as a single accident, a brief episode, a passing cloud of gas. But a second major flare followed in the year 2013, and the deeper fact was that the emission never returned to the original baseline after these events. The core did not simply shout and fall silent again. It changed. Photon energy measurements strengthened the case, because energy matters more than brightness. The X-ray photons carried signatures of heating, telling astronomers that this was not a trick of distance or dust. It was a change in physical conditions near the center, a region where gravity can turn infalling matter into radiation. That points to one mechanism: increased accretion rate. More material feeding the black hole, or feeding it differently, raising the temperature of gas close to the event horizon and pushing more energy into the X-ray band. So the assumption breaks. A black hole classified as dormant begins to look like a system that can wake in episodes, not in spectacular jets we can see with the eye, but in high-energy flashes that rewrite the baseline of the core itself. If the core can flare, what is triggering it? And if it never fully settled back, what kind of longer arc are we watching without realizing it? The story already felt intense. Heat in the dust, a central mass too large to ignore, a baseline that never fully returned. But there is one more step beyond light, a step into particles that barely interact with anything at all. Scientists did not expect signals like this from Andromeda because neutrinos are almost never caught from beyond our own cosmic neighborhood. They pass through planets as if planets are thin mist. They pass through telescope mirrors without noticing. So, if Andromeda was sending neutrinos, it would mean something extreme was happening, something capable of hurling particles to energies that ordinary stellar environments struggle to reach. The effort to listen for neutrinos looks nothing like an observatory. It is deep ice. The IceCube Neutrino Observatory watches a volume of Antarctic ice so clear that it can act like a detector. When a rare neutrino strikes and produces a fast-charged particle, that particle makes Cherenkov radiation, a faint blue flash that spreads through the ice. That flash is the message. Not an image, but a trace. And if high-energy neutrinos were detected from the direction of Andromeda during the same periods when the core flared in X-rays, the payoff would be profound. It would suggest the flares were not only heating gas, they were accelerating particles to ultra-relativistic speeds. That is the kind of acceleration expected near black hole environments, where magnetic fields and violent flows can turn gravity into a particle accelerator on a scale no laboratory can match. The deeper fact is what neutrinos demand. They are not produced easily. They usually point to collisions between ultra-energetic particles and surrounding matter or radiation, producing secondary particles that decay into neutrinos. So a neutrino signal would not just confirm activity, it would confirm extreme energy processes, the kind that make a galactic core more than a bright spot. They make it a machine, and that changes the meaning of everything that came before. If Andromeda can flare in X-rays, and if it can also launch the kind of particle physics that leaves neutrino traces, then Webb did not simply reveal warm dust. Webb may have revealed the surface glow of something far more violent, hidden behind wavelengths and hidden behind time. The pattern is hard to ignore. Webb sees warmth in dust where calm was expected. X-rays flare and the baseline shifts. The core stops behaving like a sleeping region and starts behaving like a system with appetite. But appetite is not a mechanism. The question becomes almost physical. How does a black hole actually feed inside a galaxy like Andromeda? The old expectation was simple and strangely comforting. Gas drifts inwards slowly. It falls in more or less uniformly, like fog settling into a valley. Earlier telescopes could not resolve the fine structure of that gas near the center, so the simplest picture survived. Smooth inflow, gradual heating, nothing that would explain sudden changes. Then Webb changed the view. Instead of a uniform haze, the gas appears structured, threaded into filamentary streams. Not straight lines, but paths that curve and spiral, as if the flow is being guided. Filaments that aim toward the center do not just add detail. They imply choreography. They suggest the black hole is not merely swallowing what happens to fall in, it is embedded in a dynamic environment that can deliver material in organized channels. To test that, astronomers use Doppler spectroscopy, measuring how the wavelength of emitted or absorbed light shifts as gas moves toward or away from us. Motion becomes measurable, not guessed, and when the speeds and patterns are mapped, the story can become stranger than gravity alone would predict. If gas accelerates or shears in ways that imply extra forces, then something else is shaping the inflow. This is where heavy physics enters quietly. Magnetic fields can thread through plasma, And when plasma moves, those fields can push back, twist, and transfer angular momentum. That influence can let gas lose the rotational support that normally keeps it orbiting rather than falling. As gas rubs, collides, and compresses, friction converts motion into heat, raising temperatures into the thousands of degrees. The glow that Webb sees is no longer just warm dust. It is the signature of a process that is grinding energy out of movement. And the deeper fact is that feeding may not be steady at all. Accretion can occur in episodic bursts. Dense clumps in those filaments can plunge inward, briefly raising the accretion rate, briefly intensifying heating, briefly producing the kind of conditions that match X-ray flares. In that picture, the flares are not mysteries. They are punctuation marks in a structured accretion mechanism. So the center of Andromeda starts to look less like a quiet engine, and more like a system that loads, releases, and loads again. And if that is true, the next question is unavoidable. What decides the timing? What shapes the filaments? And what happens when a feeding cycle aligns with the larger gravitational future of a galaxy already moving toward us? Andromeda no longer feels like a single object. Webb shows a core with structure and heat. X-rays flare and do not fully settle back. Feeding looks channeled and episodic. But there is a deeper reason a galaxy might behave this way, a reason written not in the center, but in the outskirts. A galaxy with a violent past carries scars, and those scars often live in the halo, where faint stars drift far from the bright disk. Astronomers suspected mergers for a long time. Big galaxies grow by absorbing smaller ones. The idea is old, the proof is hard. To prove cannibalism, you must map stars so faint and so spread out that they are almost indistinguishable from the background. You need deep imaging, the kind that stays on target long enough for a ghostly structure to rise out of the noise. That is where the payoff came. Deep imaging with the Hubble Space Telescope revealed stellar streams, long ribbons of stars arcing through the halo. Not random sprinklings, coherent structures like trails left behind when a smaller galaxy is torn apart by tides. And once you see a stream, you can test whether it is real by measuring motion. Radial velocity measurements can show whether the stars share a common drift, whether they are moving as a family rather than as a crowd. Then the deeper facts turn those streams into biographies. Spectroscopy can measure chemical composition, and chemistry is memory. Low metallicity stars can indicate origins in smaller dwarf galaxies, systems that formed fewer heavy elements before being disrupted. When multiple streams show distinct chemical signatures and coherent motion, the interpretation tightens. These are not ordinary halo stars, they are the remains of destroyed galaxies. In that picture, Andromeda is not merely a spiral galaxy with a bright disk. It is an archive of encounters. Major mergers and older mergers leave different kinds of debris, and the halo becomes a layered record of when Andromeda fed and what it fed on. Cannibalism is not a metaphor. It is the way galaxies assemble. And if this process is still ongoing, then the question becomes personal. When a galaxy spends billions of years consuming its neighbors, what does it become? And when such a galaxy is already moving toward the Milky Way, what kind of history is it bringing with it? Until now, the danger of Andromeda has sounded distant, like a calendar event placed so far ahead that it barely feels real. The collision, people said, is billions of years away, and when most minds imagine it, they imagine only one moment. Two bright disks meeting, star fields passing through star fields, a slow cosmic reshaping. But that picture assumes the galaxies begin where the light looks bright. It treats the disk as the boundary, and it ignores the part that is harder to see, the enormous halo of gas that surrounds each galaxy, extending far beyond the stars, thin enough to be invisible in ordinary images, yet massive enough to matter. Scientists began to test that hidden boundary with a different approach. Instead of photographing the halo, they used ultraviolet absorption spectroscopy with the Hubble Space Telescope, looking for faint fingerprints left when background light passes through tenuous gas. It is an indirect method, almost like detecting fog, by watching how it dims a far street lamp. The effort is meticulous because the signal is subtle and the gas is thin, but it is also persistent because halos are large. The payoff is the unsettling shift in scale. If the halo of Andromeda reaches on the order of 1,000,000 light-years, and if the Milky Way halo is comparable, then the space between the galaxies is no longer empty space. It is a region where extended atmospheres can meet, and when those halos overlap, interaction has already begun, not with a dramatic impact, but with a slow exchange of gas, pressure, and gravity. The deeper facts come from what can be measured in that overlap. Gas density, expressed as atoms per cubic meter, can be inferred from absorption strength. Motions and temperature states can hint at heating and mixing. And when the halos are already influencing each other, gravitational binding stops being a future prediction and becomes a present condition. The disks will collide later, but the encounter starts in the outskirts, where the first contact is quiet and easy to miss. So the collision is not a single event waiting in the distance. It is a process, it has stages, and it may have been underway for an astonishing length of time. Until now, the danger of Andromeda has sounded distant, like a calendar event placed so far ahead that it barely feels real. The collision, people said, is billions of years away, and when most minds imagine it, they imagine only one moment. Two bright disks meeting, star fields passing through star fields, a slow cosmic reshaping. But that picture assumes the galaxies begin where the light looks bright. It treats the disk as the boundary, and it ignores the part that is harder to see, the enormous halo of gas that surrounds each galaxy, extending far beyond the stars, thin enough to be invisible in ordinary images, yet massive enough to matter. Scientists began to test that hidden boundary with a different approach. Instead of photographing the halo, they used ultraviolet absorption spectroscopy with the Hubble Space Telescope, looking for faint fingerprints left when background light passes through tenuous gas. It is an indirect method, almost like detecting fog, by watching how it dims a far street lamp. The effort is meticulous because the signal is subtle and the gas is thin, but it is also persistent because halos are large. The payoff is the unsettling shift in scale. If the halo of Andromeda reaches on the order of 1,000,000 light-years, and if the Milky Way halo is comparable, then the space between the galaxies is no longer empty space. It is a region where extended atmospheres can meet, and when those halos overlap, interaction has already begun, not with a dramatic impact, but with a slow exchange of gas, pressure, and gravity. The deeper facts come from what can be measured in that overlap. Gas density, expressed as atoms per cubic meter, can be inferred from absorption strength. Motions and temperature states can hint at heating and mixing. And when the halos are already influencing each other, gravitational binding stops being a future prediction and becomes a present condition. The disks will collide later, but the encounter starts in the outskirts, where the first contact is quiet and easy to miss. So the collision is not a single event waiting in the distance. It is a process, it has stages, and it may have been underway for an astonishing length of time.